Alright, so in this lesson we're going to start talking about circular orbits when we start looking at orbital motion and what we really mean when we talk about a circular orbit. So to talk about a circular orbit, what we can use is Newton's law of gravity, which is the way Newton described gravity to define a circular orbit. The object must be moving at a constant speed v in the orbit in order to remain in a circular orbit. If that speed v changes, it would actually change the shape of the orbit from a circular orbit into probably an elliptical orbit. And we'll talk about that in the next lesson, how that would work. Remember that Newton's law of gravity is g, which is the universal gravitational constant, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, times the product of the masses of the two objects divided by the radius or distance between the two objects squared. What I do is set that equal to centripetal force. Say gravity is responsible for centripetal force, mv squared over r, where the little m is the mass of the object that's in orbit. What happens first is those m's cancel out and you end up with this equation. And if you do a quick square root, you figure out what that speed has to be in order for this orbit to remain a circular orbit. So the thing to point out with a circular orbit is if you're in an orbit which is a circle, you're at a constant speed, and that speed is really determined by really only two variables: the mass of the object you're orbiting around and the distance from the center of that object you are. Now we can calculate the period of a circular orbit by saying period is equal to 2 pi r over v, where 2 pi r is the distance around your orbit, one time around that circle, and v is the speed you're in that orbit. If we plug in what we know about v, remember that v is square root of gm over r, so this would be square root of r over gm, and square everything to get rid of the square root. What you end up with is that period squared is equal to 2 pi squared times radius cubed, because there's a radius to the 3/2 in here, times g over m. And so we could say for sure about a circular orbit is the square of the period is equal to the cube of the radius of that orbit. Keep that in the back of your head for the next lesson, because that comes up in another place as well, which is also pretty cool. This comes up again. So let's look at problem G1, and let's say we have a geosynchronous satellite, which are the ones that are used for communications here on Earth. The reason why they're important is that they're located over the same location over the Earth's surface at all times. So if I know that a geosynchronous satellite is sitting right overhead over Faribault, Minnesota, I can look up right overhead over Faribault, Minnesota at any time of day, any time of year, any day of the week, and that satellite is straight up over my head. That's how, like satellite television, you can have the satellite dish that's pointed in one direction all the time. That's because that satellite that is actually sending that signal is a geosynchronous satellite. What this means is that these satellites make one orbit around the Earth every time the Earth makes one revolution. So they basically have an orbital period of 24 hours. They go around the Earth one time for every time the Earth orbits on its axis. That way, that satellite is always over the same location of Earth at any given time. Let's see if we can find the distance that this satellite is above the Earth's surface by using the fact that its orbital period is 1 day, or 86,400 seconds. So let's use this idea that period squared is equal to 2 pi squared times r cubed over gm. Things about g, we know what g is, and we can look up what the mass of the Earth is. It happens to be 5.98 times 10 to the 24th kilograms. If we solve this for radius, basically I've multiplied everything by gm and divided by 2 pi squared, and then I take the cube root of everything and plug all my numbers in, I get that this satellite is 4.23 times 10 to the 7th meters above the center of the Earth. Well, this said above the Earth's surface, so I need to subtract the radius of the Earth, which happens to be about 6.31 times 10 to the 6th meters. And so I get that these satellites are 3.6 times 10 to the 7th meters, or what is that, divided by 1,000, 3,600 kilometers above the Earth's surface. Now the second problem that I have, and I forgot that I didn't do any animations here, I'm sorry, is we have the International Space Station, and it's in orbit about 254 miles above the Earth's surface, which seems like a long ways, but it's actually close enough that you can see it from the Earth's surface if the light is right. I've actually seen the International Space Station a couple of times from the Earth's surface. Both of them happen to be at dusk, where the sunlight is coming at the right angle that it reflected off kind of the big solar panels on the space station. You see that reflection here on Earth. And what I want to know is, what is the orbital period and orbital speed of the International Space Station? So what I did was I said, well, the space station is 254 miles above the Earth's surface. That happens to be about 4.069 times 10 to the 5th meters, which is much, much, much closer. What is that? Divide by 3, 406 kilometers above the Earth's surface. That's much closer than the thousands of kilometers that my International Space Station was, or that my geosynchronous satellite was. Now, if I take my radius of the Earth, this is the distance from here to the center of the Earth, and add the distance I am above the surface of the Earth, we get that piece of information there. Now, if I plug radius, how far I'm above the center of the Earth, and g and m into my velocity equation, I find that the International Space Station is moving almost 7,700 meters per second. That's pretty darn fast. If you actually work that out, that's 7.7 kilometers per second. That's more than, that's almost 4 miles a second if you want to be in the English system. That's pretty fast. If we figure out what its orbital period is, I can do 2 pi r, which I now know, divided by speed, and I find that it's 5,550 seconds, which ends up being, well, a little more than 1.5 hours. I can tell you the orbital period of something that's at the orbit of the International Space Station happens to be something about 93 minutes, which seems to work out here about 1.54 hours. So this is a couple quick problems that we can use a circular orbit to begin to predict the problems we'll look at in the next lesson is a set of rules that we use in order to predict orbits that are not circular orbits.